Okay, shall I start? Okay, so let me just find a piece of chalk. So actually, what did we do? So in the last lecture, we finished off talking about Ito calculus. We were considering a system of interacting Langevin processes. Okay, and so the idea is that we started off with the following. So basically the particles they had some diffusion constant. So they have a pure Brownian, so that's the pure Brownian part, and they were basically in a potential, so which can depend on time. So we looked at that, and the sorts of, so we have, so we had n of these. Okay, so they're all buzzing around and they're interacting via this potential. And there's a dt here. Okay, and so you want to study this system, and so rather than studying these n equations, what we saw was in the case, well, for a particular case where ux of t was given by, so it had two terms. It had an external potential, which I'll call nu of x. So it could be due to some applied electric field. This works for forces as well. And we also had a term which was the potential. So the local potential would be the sum I equals 1 up to n, the gradient, so v of x minus xi. So there's pairwise interactions between these particles. So every particle sees this potential, right? And I was talking about this, you know, the particle doesn't really see itself, but if we say the gradient of v is equal to 0, it doesn't have any force on itself. So that was the first thing. So I introduced after I derived the equation, I introduced a density functional h of rho, which was t, the integral over all space, rho log rho. So we were saying that this looks a bit like, this is like minus Ts, because this is the entropy of the density. So rho is actually, in the calculation we did, it was the sum, it was the density field. It was the sum I equals 1 up to n, a delta function at the point x minus xi. So it's a delta function peak where you have every particle. And then we had a term which was a half the integral of rho of x, v of x minus y, rho of y, dx dy, and then the term that comes from the potential. Okay? And so what I showed is, in this case, if you look at this density field, the density field actually obeys a partial differential stochastic equation. So it has a term that looks like this. And it has another term, it has a noise term, which is given by the divergence of the square root of 2d times the density field times eta of x. Eta of x of t. So this is a vector white noise field. So in terms of its spatial vector components, it has this correlation function. So everything's delta. So it's delta alpha beta, delta of x minus x prime, delta of t minus t prime. Okay, so what you've done is you've taken from a microscopic model, you've taken this microscopic model and we've derived an exact equation for the evolution of the density field, okay? So you've probably seen equations like this before. Has anybody ever heard of model A or model B in phase ordering kinetics? Okay, so in phase ordering kinetics, you have some sort of an order parameter. So phi, you can think of phi as being some sort of volume fraction in two phases, you can think of it as being some Ising parameter, which is plus or minus 1. So often you have a field theory okay. So what you can do is you can introduce some sort of Hamiltonian free energy density functional for this. So for instance, this is the one that everybody writes down for phase ordering kinetics. You have something like this. You can have something like this, okay? Look at some sort of Hamiltonian, this form here. Okay, so you want to get a Gibbs-Boltzmann distribution which in equilibrium you have the probability of seeing the field phi is equal to e to the minus beta h of phi. Okay, and if you look at there are two sorts of dynamics. The easiest dynamics, so I wrote down a functional Fokker-Planck equation for this, and I showed you that the correct equilibrium distribution was P of rho is equal to e to the minus beta h of rho. Okay, so you can write down a functional Fokker-Planck equation, or you can make your model discrete as well. You don't have to necessarily play around with functional derivatives. You can make with things like this, you can make your model discrete. So in order to get this equilibrium distribution, so basically you want to minimize naively you want dH by d phi to be at around 0. So there's one type of dynamics, you would take d phi by dt is equal to, so I can write something like minus eta times d times the functional derivative of dH by d phi of x plus, so if I want to get things right, I put square root of 2d here, and then you have just a scalar field here, e to x of t, okay, where eta x of t, written this way, eta of x prime of t prime, this is just equal to delta of t minus t prime, delta of x minus x prime. Okay, so that's, you can check that basically, I mean, you think of in terms of discrete systems, right? You can have some sort of matrix operator here, and basically, if I look at this as an operator, it's basically a delta function. Okay, if I look at the correlation function, it's a delta function when I operate here, and it's basically a delta function which is acting on dH by d phi of x. So that's called Model A dynamics. You can see the problem with that is, so the problem with that is you can see that the overall, if phi really was an order parameter, if you were looking at a lattice model, if your underlying model was a lattice model where particles basically moving on a lattice, you can imagine an Ising model where the ones and minus ones moved around on a lattice, you see that the overall magnetization would be conserved, right, if you're just moving particles around. The problem here is that if I integrate over all of space, this term here is going to fluctuate, right? So this is a model that would be more useful for something like Glauber dynamics, where you randomly change spins, okay? So you can really flip spins and transform them. And so the problem with this dynamics is it doesn't conserve the order parameter, the average value of the order parameter. So basically phi dx is not conserved. Okay? And then in order to fix that, there's another type of dynamics you can write down. So you can write down something like this. So d beta. Laplacian is a negative operator. You want something which is dissipative. Okay? And then you have something like plus the square root of 2d, the divergence of a vector noise field. So here you introduce a vector noise field such that eta of alpha of x of t, eta of beta x prime of t prime is equal to delta of alpha beta, delta of x minus x prime, delta of t minus t prime. So these are, and then you can go and extend this. You can couple these models to hydrodynamics. So this model here, you can see if I look at the correlation function of this operator here, if I look at the the correlation function of this, then it's basically Laplacian. So I have this guy. So basically, when I square this correlation function up here, it's basically proportional to this guy here, and that means that you get the right Gibbs-Boltzmann distribution when you do the exercise writing down the functional Fokker-Planck equation. So this guy here is called model B. So if you're looking at, so there's some coarse graining, obviously. This doesn't come from a microscopic model. I mean, one thing you should notice about model A, so the big difference here, if you look at this model here, so this is the SDFT, okay, it's that the noise here is multiplicative, whereas it isn't here. And actually, but the noise has to be multiplicative. If I'm looking at a system, if I create a hole in my system, right, if I just somehow create a big hole, then obviously the density field can't evolve, right? So if there's a hole here, it's going to take time for particles to diffuse into this region. So obviously nothing can happen here, right? So basically the vacuum is preserved by this dynamics, okay? If rho is equal to 0, then you don't have any dynamics, okay? Okay, so that's what I wanted to say about that. So in the last lecture, I showed that, so I didn't really finish the calculation with the functional Fokker-Planck equation, but I think it's in the notes, okay? Yeah? Yes, so you can see that, right? Because if I integrate this over a periodic system or a system, so the point is that this has the form, this equation here has the form, right? d phi by dt is equal to minus the divergence of some current, right? So if I look at a periodic system or I impose no flux on the boundary of my system, it's actually quite complicated to impose no flux in simulation, so it's better to think about periodic boundary conditions. So here we have the order parameter. I mean, the order parameter would be, strictly speaking, 1 over v. Yeah, it's an intensive quantity. Here it's conserved. So if you do dynamics in this sort of system, if you have two phases, 1 and -1, basically what will happen is that if you're below the critical temperature, then one guy will win, right? Whereas in this system here, because of conservation of the order parameter, it will phase separate. You get an interface between the two phases. Okay. So we saw that the statics, we have this very strange looking field theory. Okay. So that's the, so this is slightly worrying because you might think, okay, this looks like mean field theory, right? You say, how on earth, you've got interactions in your system, this looks like mean field theory, but what you should remember is that mean field theory, so this rho is actually a fluctuating field in my functional integral. So mean field theory is actually, you write down a functional for the average value of the density. So rho bar is my notation for the thermodynamic, the local average of rho, right? And so mean field theory is this. Okay, so you replace all these averages by their rho bar value. Okay, and then you do so dx dy, and then you basically say that the equation that gives you rho bar is that dh mean field by d rho bar is equal to 0. And so, sorry, there's rho bar here, right? So when you do this equation basically tells you, so if I minimize this equation, I'll do it quickly, you get an equation that looks like rho bar of x is equal to some constant, okay, some rho 0 times e to the minus, so you divide by t here, e to the minus beta v of x. And then this term here is the local potential, so this is minus a half, minus the integral of v of x minus y, rho of y, dy. Okay, so this is you can call this phi, the local potential. So this is okay. This is if you do electrostatics, this would be the electrostatic potential. This would be some imposed potential. This is basically the Poisson-Boltzmann equation. Okay, so this is mean field theory. And if I were looking at a field theory with this action, obviously I would write that rho is equal to rho plus rho bar, and then I would do my loop expansion, right? So the mean field theory is recovered immediately just by looking at the saddle point. So the sort of more phenomenological mean field theory is derived directly from this. So that's one thing. And actually, there's a link. When you look at this equation, when you look at this type of equation, when they were first derived, actually, the people in chemical physics, actually, they said, well, they don't like the noise. So what they were doing is they were throwing the noise term away, and they were actually trying to write down, there's something called dynamical density functional theory, which is, this is partly the starting point. And the problem is that when you take the average value of this equation, you want to take the average value of this equation. The only problem is that the noise will go to 0, but you have this interaction term, right? You have the rho term. So the idea is to try and write the correlation function of rho in terms of rho bars. And so that's called dynamical density functional theory, which so that's why I differentiate it from stochastic density functional theory, okay? So it uses results from equilibrium statistical mechanics to close this dynamical equation, okay? But it's only really interesting in non-homogeneous systems or out of equilibrium systems. So if you're interested in colloids, in gradients, or under some sort of external driving, you can do that. So you can use there is a mean field version of this, which is called dynamical density functional theory. And I'll put the reference to that in the notes. Now, there's another approximation. So the thing about what I just wrote down, the mean field equation I wrote, okay? Mean field is really useful in systems where you break the symmetry, right? If you look at problems of electrostatics, if you look at electrolytes between two charged plates, if the charges on the plates are quite strong, mean field theory gives you actually quite good results, okay? We know that mean field theory doesn't work for phase transitions because mean field theory is boring in the bulk, right? But if you have charges on plates, then actually, it builds up a mean field, okay? It forces there to be a mean field which is non-zero, and then fluctuations about that can become relatively small. So mean field theory actually works quite well for electrostatic systems, okay? But if you look in the bulk, then obviously there's no external force. You can see the system is isotropic, so this potential is invariant. So all mean field theory tells you in the bulk is that the average value of the density is equal to the average bulk density, okay? So mean field theory is dull in the bulk. So that's no good. So what you want to do, there's something else you can do in the bulk. Okay, we're basically just saying the average value, the local value of rho of x is equal to rho bar. So this is what we're going to call the bulk density. Okay. So what I'm going to do is I'm going to look at fluctuations about the bulk density. So that means I'm going to write that rho of x is equal to rho bar plus n of x. So n of x is just the fluctuation, right? Rho of x minus rho bar. By definition, because you should have that the integral dx of n of x is equal to 0, okay? Because this is rho bar, then obviously this term has to be 0 when I integrate over all the volume of the system if I have a finite system. Okay, now if I substitute this into the expression I had for H, so you remember I was saying that rho log rho is not nice in a field theory, and you wouldn't really, don't like writing it down. When I do this, so let me have a look. If I take H of rho, this is equal to, so because I'm looking at a bulk system, let me take V of x, little v of x is equal to 0, okay? A bulk homogeneous system. So H of rho is equal to this. So if I expand, so I put this into the rho log rho term, and I do the calculation. So basically I have T log rho bar plus n log of rho bar plus n plus a half rho bar plus n v of x minus y rho bar plus n. So this is n of y, this is n of x. Okay, so actually if you look at the terms which actually explicitly depend on n, and you use the fact that the integral over, use this fact here, you actually find that this, so expanding to order n squared, okay, there's no order n term. You can verify the order n term cancels or gives you a it doesn't contribute. You find that what we're going to sort, so we call this HRPA then. So this is called the random phase approximation. For a reason I've never really understood, because I think there's some sort of approximation that was used in quantum mechanics, but they carried on using this notation in liquid theory. Do you understand why they call it the RPA? Anyway, so when you do that, what you find is it actually becomes a quadratic Hamiltonian. So I can write it in this form here, dx prime, n of x, delta of x minus x prime, n of x prime. Okay, so you have a quadratic theory for the density fluctuations. A Gaussian theory. Peter was complaining that you can't send the blackboards up. So it depends on your size, right? I guess Peter was using the top half and I'm using the bottom half. Yes, I'm going to tell you what the delta is. Sorry, I got distracted. So delta of x minus x prime. So you can see that when you expand this term here, see you're going to get a term of order n squared here, right? The term when you do the expansion of the n, there's an order n term here which goes to the order n term here, and there's an order n squared term which goes by the rho bar. But this term is completely local, right? So this local term basically gives you, so this, because I'm using this delta notation, this is t divided by rho bar times delta of x minus x prime. So this is a completely local term. And then the interaction term just gives you v of x minus x prime. Okay, so this is what it looks like. So basically your field theory looks like a Gaussian integral, right? So you have something up in the exponential. And so if I want to calculate the correlation function of these density fluctuations are Gaussian, so really the only thing I need to know about them is their correlation function. So can somebody tell me what... So the random phase approximation is what actually, so what I will, it's the result of this calculation. Well, actually, so all I'm doing for the moment, the approximation I'm making is I'm expanding the density and I'm forgetting the higher order terms, right? Now I'm going to calculate the correlation function. And the form that I'll find for the correlation function is what's known as the random phase approximation. So I'm saying that this expansion is mathematically equivalent to the random phase approximation, okay? So, so that's the HRP. So, okay. And now if I calculate this, so I have e to the minus beta h. So h is my Hamiltonian. So basically I have equipartition of energy. This tells me that C of, so C of x, the correlation function is equal to the expected value of n of x. I mean, it's invariant by translation, so I can take, when I can compute my correlation function, I take 1 point at the origin, 1 point at x. That's just equal to T, the temperature, times delta to the minus 1. Okay, yeah? Yeah, it is trivial, yes. I mean, all I'm doing is, you can see, okay, so let me just say a quick word about it. So, okay, so there's a term here, which is the rho squared term, but that's a constant. I can just throw it away, right? I only want, you can see that I have an nx, ny term here, right? So this is the term that I wrote down. This is the term here. If I write out explicitly what the, you see, this is the term that gives me this. You can check the cross terms go to 0 because when for instance, if I look at the term rho bar v n of x, there's an integral over y, but but integrating this v of x minus y over y, I can shift the coordinates, so this is a constant, so this becomes an integral over x, right? And the integral of n of x dx is 0. So the other guy disappears. When I expand the log, so I have a rho log rho bar term, rho bar log rho bar, which is a constant as far as n is concerned. I have a term here which is n rho bar, which gives me nothing. When I expand here, I have a term n rho bar. And so I actually, when I do the expansion, the first term, I get one term which is n times n divided by rho. So that gives me n squared divided by rho bar. And then when I look at the next term, I have minus n squared divided by rho bar squared, and that's the term that gives me a half, right? So it's not, there's nothing particularly sophisticated. It's just it's a simple expansion, okay? So you basically find that, so you basically, if you have a Gaussian theory, right, you know that if I look at the expectation value of the field is just the inverse of the, okay, if I write, for instance, it's just, if I have Gaussian random variables with a inverse correlation matrix, that what's in the measure for Gaussian random variables is the correlation function to the minus 1, right? Okay, so this is a standard result, and the t is coming from the fact that I have a beta that goes with the h. Okay, so this is what I find, and so when I write delta minus 1, what do I mean by delta minus 1? This is to be understood in the sense of an operator. Okay, so delta minus 1 is defined as, if I look at delta of x minus z, delta minus 1 of z minus y, so this is like matrix multiplication, okay? So it's whenever you go between functions and matrices, the sums on indices in matrix multiplication, they become integrals. So z is my sum variable here. So this is the identity, and what's the identity in function space? It's the delta function, yeah, it's the direct delta function, because you have to, okay, so it's delta of x minus y. So this is my identity. The other thing I can define, actually this thing looks nicer in Fourier space. So in Fourier space, I can look at the correlation function of the Fourier transform of the density fluctuations. So this object gives me what's known as the static structure factor. Okay, and you can work out, this is just equal to 2 pi to the d, where d is the dimension of the space. There's a term which is delta of k plus k prime. Does anybody know why we always have it? Where does the delta of k plus k prime come from when we look at correlation functions? It comes from the the fact the correlation function just depends on a single coordinate, right? It's the invariance by translation in space. So this is because we have a spatially translationally invariant system. And so you have this, and then this is S. This is called S of K, okay? So this S of K is known as the structure factor. Liquid state theory. Okay, so that's it. And now if I want to calculate, so an S of K is just, it's the Fourier transform of C tilde of K. Okay, so C tilde of K, so this is equal, so C tilde of K is equal to what? So it's T, the Fourier transform, everything becomes diagonal now, so this is just T times 1 over delta tilde of K. So this is equal to T times rho bar divided by T plus rho bar beta times V. Sorry, T plus beta rho V of K. Okay, so I can divide by beta, so this is just equal to rho bar divided by 1 plus rho bar beta B tilde of K. Okay, so this is actually called the random phase approximation. It means that when you the fluctuations in your system, you're basically using this approximation to approximate this. Okay, so this is the RPA. There are lots of different ways to derive it. If you've done virial expansions, then it corresponds to doing summing a geometric series, actually, and then taking a low temperature limit. Okay, so there are lots of different ways of getting this. Okay, so this is the RPA, and the interesting thing is, so for the moment, I'm only talking about, all these theories look quite, relatively trivial for one species, okay? And if you look at the generalization of this to 2 species or 3 species for electrolytic systems, so for electrolytes, okay, if you do this approximation, you find something which is called the Debye-Huckel approximation. We'll talk about that in the last lecture when I talk about electrolytes. So this is this linearized theory is actually, and the Debye-Huckel theory, there are certain limits where it works very well, and from a practical point of view, people are doing biophysics there. They're using the Debye-Huckel theory all the time to have a simple analytic theory that gives you an idea what's going on. So what I'm going to show you is that we can basically find a dynamical equivalent of the random phase approximation. So we need, okay? Okay, but there's a, so actually how we might see, that this is quite interesting because, so imagine we have some sort of free energy functional. So if I write, so I have, imagine I look at, I have this free energy functional rho, okay? Let's just accept, it doesn't have all the information in this argument. So it describes, it gives you a free energy for this system which you want to minimize, okay? And so you're not in equilibrium, okay? You're out of equilibrium. So you look at some sort of out of equilibrium configuration. You want to know what the currents are in the system. So this is this is actually quite a good argument to derive things like stress tensors and body forces, right? So you have an out of equilibrium configuration, right? I want to know what the local body forces are on each point in this system, yeah? So I want to have so how do I work out the local body? So here we generically have that dH by d rho is not equal to 0, okay? So I'm looking at a system where dH by d rho is not equal to 0. So I know that something must flow, right? So the problem is I can't really do anything. But what I can do is I say, imagine I have a very intelligent demon, right? A sort of more sophisticated than Maxwell's demon. And what he's going to do, he's going to come along and he's going to pose a potential, right? He's going to come and he's going to impose a potential on the system, which actually puts the system in equilibrium. So everything freezes, right? So in this zero noise limit, dH by d rho will be equal to 0. So my little devil comes in and he's going to apply some sort of field which I'll call mu, which isn't exactly the chemical potential, it's minus the chemical potential. So I'm going to look at another functional, j of rho, and that's going to be, well, h of rho, and then he's come in and he's applied some sort of, it could be an electric field, okay, for mu of x times rho of x dx. So he's come in and he's applied this potential. Okay, so locally he's just looked at what sort of potential he needs to put to put every particle in equilibrium, right? Does everybody understand what I'm doing? So I'm basically just imposing, I'm bringing in a potential well, and I'm just going to go and cancel out all the local forces in this system by applying this potential, right? So what is this potential? How do I know which potential that I need to apply? Well, it's easy. I must have that dj of rho pi d rho, that must be equal to 0 at every point, yeah? So if I look at that, that tells me that the potential that the demon needs to apply is equal to minus dH by d rho of x. Okay? Now, if I apply a potential in a system, the local body force generated by mu, well, this is a potential, so this means it must generate a body force, Fb, which is equal to the local density. I mean, think about electrostatics, if you times the gradient of mu of x, right? So that's the body force generated by mu. Okay? In electrostatics, if I apply a potential, phi, then the local force is rho times, local force density is rho times E. Okay? It's the electric field if I'm talking in terms of charge densities. Okay, but actually this means that the local body force acting on the system out of equilibrium, so the local body force out of equilibrium generated by the system on itself well, it must be minus that, right? Because this was cancelling. It must be F body self, which is equal to rho times grad mu. Okay? Yeah, the minus sign has changed. Okay? So basically, I mean, I'm deriving the chemical potential because I'm changing the sign, right? Just telling me which way that so it's telling me which way the current is flowing. So then if I do that, if I say, I make a phenomenological argument, I say, well, okay, I have a local body force. This must generate a current. So yeah, that's right. So the current J must be equal to kappa, where kappa is the particle mobility, times the body force. Okay, so this is the current, the particle current. Okay, so that's what you have there. So this is equal to, so now if I use the equation rho dot plus the divergence, so I use the conservation of matter. I look at that, it basically gives me the equation rho dot of x of t is equal to the divergence of kappa rho of x times the gradient of dH by d rho of x So this is an argument in one of Kawasaki's papers where this equation was derived phenomenologically. Okay, so this is the... Oh, the dot is not very clear, and I must admit I should use the partial derivative. That's true. Dots are not a good idea, right? Actually, blackboards being dirty like that are good for me when I'm lecturing in French and I don't know where the accents are because you can't see the accents anyway. So the other tip for anybody if you have to give a lecture in France and you can't remember if it's an acute accent or a grave accent, is to write the accent like that and let people decide for themselves. Okay, so this is the equation that we've got, and of course remember that kappa is equal to d times beta, the link between mobility and diffusion. So this is the equation you've got, but this hasn't given me the noise. I'm talking about, there's no noise here, I was talking about an equilibrium argument. So then of course, what you then say is, well, I have to have a noise here. Okay, so let me put d beta here. And if I write down the functional Fokker-Planck equation, the noise that I must choose this noise here. So that's another way of driving it. So this is a sort of more a physical argument for what happens. I don't know if it's clearer I mean, the problem is that you don't know what H is, right? Because why should you then go and say, I mean, you might guess, well, what do I need? If I want to get the diffusion equation, that tells you need a rho log rho term, right? So this is a sort of more physical way of getting the argument, based on the idea of the current having this linear response form due to the body force, okay? So that's another way of doing it. Okay, good. But it's certainly quicker, right? But it's not exactly a back-of-the-envelope calculation. Now, there's this story about Richard Feynman, that he used to talk to his colleagues and show them calculations on the back of envelopes. But when he went into his office, the cleaning lady would see that, you know, they've all been written out neatly, then it'd been transcribed to the back of the envelope. Okay, so let's have a look at, so let's see if we can, stochastic density functional theory, so this is 2.4, SDFT in the limit of small density fluctuations. So what I want to do with my SDFT now, so I'm going to look at the bulk case, okay? So this means there's no external potential. So the starting point is, again, you write that rho is equal to rho bar, which is a constant, plus n of x. And then the equation for the fluctuations, so now I'm looking at to order n, you basically find that dn by dt is equal to d. Then you have the divergence. So I'm just taking the equation that I wrote earlier. So nothing happens, the del squared rho term, okay, the rho bar goes away, so he's just going to get the gradient of n here, right? And then we have the term that comes from the interactions. And what you're going to get here is actually beta times rho bar. Remember, you had rho times the gradient term, right? So this is just the first expansion. So this is rho bar plus n. Okay, so you have rho grad u, so this is the rho bar that comes from here. And then you have the integral, okay, so I noticed integrated over y twice, that's what's, I'll give you my notes when I've, so here you're going to have the gradient of v of x minus y times n of y. And then you're going to have the noise term, and what I'm going to do in the noise term, so it's actually, I'm going to take, so I had rho here, right? So I'm going to write 2d times rho bar. So in principle, I should have rho bar plus n, but actually, I'm just going to not take the n term. I'm just going to replace the noise by rho bar. This is going to have a number of important consequences. The model is going to become soluble, and also the approximation is going to become consistent with the random phase approximation. Okay, we'll see that. Now, can anybody... So when I was doing this expansion, this was the term, so this is the term gradient of u, right? So in principle, I should have had a term, well, I had a term plus n here, right? But I have the terms with two n's, well, that gives me n squared, right? So I throw that away. And remember, I should have a rho bar here, okay? But the rho bar term, actually, when I integrate gradient of v over all space with a constant, that term gives me a 0. Okay, so the only n you see in the calculation was the n which was actually generating the field. Okay, so the term, what I'm trying to say is that I had a term which looked like rho plus n. Okay, I'm saying that when I do the integral over y, this guy gives me 0, okay, because it's the gradient of something which is spherically symmetric. Okay, so that gives me 0. So the only term, so this guy had to go with him, so he disappears, so the only guy I get is this guy here, okay. So that's the equation. Now, why have I said, so this is consistent to take this approximation, because if I take this equation, I find that dn by dt, I can write it as, so I have my d here, I have a rho bar, and I can write this as the gradient of dh by d rho in the random phase approximation, so for the quadratic Hamiltonian. Okay? And you can see that this choice, rho bar times d here, okay, so it has this form. So you see that when I square up this operator here, this noise has as an operator, when I square it up, it actually gives me this term here, so I get the right Gibbs-Boltzmann distribution. So this gives the correct Gibbs-Boltzmann of equilibrium guilt. In the RPA, okay? Okay, so otherwise you're making an approximation, you're saying the fluctuations in the density are small statically and dynamically. If you were to do anything else with the noise, then the theory wouldn't be consistent because you'd write down a dynamical theory which didn't agree with the static theory, okay? Oh, it's the derivative with respect to n, yeah. At the point x, yeah, sorry. Yeah? So this is what I said earlier. See, what I'm doing is actually often when you look at, if you look at things like fluctuating hydrodynamics, there are lots of theories where you basically do a sort of mechanical calculation which implies the system is at 0 temperature, right? So I'm somehow assuming that this system is, I'm doing a sort of mechanical calculation, right? I'm ignoring the noise, okay? Right, so what you do is you write down the deterministic part of the equation that you would have if you had no noise, right? And then you add on the noise, but the way in which you add on the noise, you write down a noise which gives you the correct equilibrium distribution, okay? So actually, if you look at, I'm trying to think of other examples. If you do fluctuating hydrodynamics, okay, there's a way of doing the Navier-Stokes equation. This might be useful for Menon. There's a way of doing the Navier-Stokes equations with noise, right? So you can actually do fluctuating hydrodynamics, or at least it's quite easy to do in this limit of Stokes flow, okay, where you linearize the Navier-Stokes equation, you throw away the inertial term. So, but what you can do is you can actually do calculations. For example, you're interested in how a membrane is fluctuating, okay? You can actually write down the equations of motion by solving the 0 temperature Navier-Stokes equations, okay? This gives you, for instance, an equation for how a membrane would float on water, okay? But this equation is purely dynamical, right? There's no noise in the equation, okay? So I'm assuming that it's a zero temperature calculation. So you do a calculation which is effectively at zero temperature, which gives you this term here, right? Which ignores fluctuations, okay? And then you add the noise on by hand. And you know what the noise must be, because if you can write down a Hamiltonian for your surface, okay? The equilibrium distribution has to be e to the minus beta times that Hamiltonian. So this is used in lots and lots of contexts, okay? You do the noiseless calculation, and then you don't have to derive the noise. You can do it directly as well. I mean, if you take fluctuating hydrodynamics, for instance, you can, really try and do the calculation with the noise, but at the end, the test of your calculation is, do you get statistical mechanics back? And if you don't get statistical mechanics back, then the referee, your paper, tells you that, sorry, go away, okay? You have to do something again, okay? If the referee reads the paper. Okay, yeah. The low noise limit. Well, so the low noise limit, the low temperature limit, you mean this? Well, yeah. Yes, well, in principle, it. Oh, you mean does the fluctuation come? No? The fluctuations aren't justified by the no noise. You probably need more noise. It's it's higher temperature. Actually, what you're doing is you're hoping that the fluctuations are small, right? You want them to be small, right? So you write down a theory. You say the fluctuations are small. Well, how do you know if the fluctuations are small? How do you check afterwards that the fluctuations are small? Well, I mean, you write down a theory, right, and you hope that it works as well as it can. But at the end, you assume that the fluctuations are small. So the average value of the fluctuations is 0, right? So that's no good, because, okay, they can be big, but on average 0. So the way you estimate the size of the fluctuations is from the correlation function, right? You look at that. Okay? So, so perturbatively, I mean, you calculate the correction to something due to the fluctuations, right? That's the problem with perturbation theory, you see, because, if the correction is big, it means the perturbation theory. So you think, oh, I found an important physical effect. No, your perturbation theory is obviously wrong, right? So actually, we'll see if we look at electrolytes, the thing that's interesting is that you can look at electrolytes, you can force them out of equilibrium, so you can have a theory for what happens in electrolytes when currents flow. And the nice thing about that is it's an out of equilibrium system, and when you put the current in, it actually makes the fluctuations smaller. So your perturbation theory actually works better for the system that you're interested in than for the static system, okay? So, good. Okay, so we have a theory. So you can see that now this is a linear theory. So actually, so let me just say something about how so this is just, so let's have a look at a general calculation for a Gaussian theory, okay? This is dynamics with some sort of noise. So let's do it for matrices, right? Because it's always good to go and see how things work for finite dimensional systems. So you can see that this is a model B type theory because there is no, this looks a bit like, this is model B dynamics, okay? Because the noise is just the divergence of eta. So this is an effective model B. Okay? So if I have so what it has the form. So if I look at a sort of example, a finite dimensional example. Okay, so let's just write down the equation of motion. So I write down something like x dot is equal to minus RA plus a noise. Okay, and I'm going to take the noise, this noise here, I'm going to take its components to be such that zeta I, zeta j is equal to Rij times 2. So this A is basically beta times some energy matrix, okay? So this is the system that I'm interested in. Sorry. So this has 2 times. This is time t and at time t prime. So this is delta of t minus t prime. So this, I'm doing it in the Langevin formulation. It doesn't matter because the noise is not multiplicative, okay? So if I, sorry, and there's an x here, okay? Right, that makes it, yeah, otherwise it's a bit of a strange equation, right? A is a matrix. Let's say A is a matrix, okay? A is a matrix. So, you know, so in this case, A would be equal to beta times h. So if I had a quadratic model, sorry, A would be equal to the derivative. It would be d by dxi of beta times h, okay? And R is some dynamical operator, okay? So this is, so if h is a quadratic Hamiltonian, sorry, what I'm saying is that d by dxi of beta h would be equal to A times xi. Okay, so this is a quadratic matrix. So let's just leave it in this form here. So if I want to solve this equation, what I do is I take this guy, so the matrices, so I can exponentiate matrices, so I write this equation as d by dt of, so what I'm going to do is I'm going to write this as e to the minus t r, so plus t r a. So this is the exponential of the matrix. Okay, yeah? Yeah, sorry, so this is, yeah, so this is equal to the component, yeah, this is equal to A, I, J, xj, yeah? Okay. Okay, so this, so I'm using, so that's okay. So when I differentiate this, this is the exponential, so you can see that this gives me exactly the terms that I had before, right? So I've just multiplied everything up by that. This is just like how you integrate first order differential equations, right? Just applying it to matrices. And so now I can solve that equation. So the solution to this equation is that x, if I write it out in components, xi of t, so I integrate this and then I multiply both sides by e to the minus tra. So I'm going to get e to the minus tra, okay, acting on x of 0, right? The initial coordinate. So if I want to write indices in here, and this is, the coordinate here is I, so I'm looking at the indice ik here, right? Okay, so it's just e to, I'm putting indices in because it's easier to do when you look at the noise. So that's the constant term for the starting point. And then you have the integral between 0 and t. And so now you have the integral of d of s, e to the minus tra. So this is the matrix coming from the other side when I'm multiplying by it. So this guy here has indices I and k. That's multiplying the exponential of e to the sra k l zeta l of s. Okay? So that's the formal solution. Now, the first thing I can do, what is really easy to do, is to calculate the correlation function, right? So if I imagine I have some sort of steady state, if I want to calculate the correlation function, I can look at Cij of t, which is equal to the expected value of xi of t times xj of 0. So in order to compute that, all I have to do is take this equation and multiply it by xj. Okay, so if I multiply it by xj and then take the average, you can see that this noise, we said that this Ito noise is always independent of the current state of the system, right? So when I take the average here, it gives 0. Okay, so I multiply by xi0, but these numbers are pulled out of the computer once I know what xi of 0 is. So the only term that I'm going to get is e to the minus t ra. And this is ik. So then I get xk0, xj0, right? And they're random variables. That's just the correlation function at 0. So this tells you that Cij of t is equal to e to the minus r tra times ik ckj evaluated at 0. So this just, you can write this in a purely matrix way. C of t is equal to e to the minus tra c of 0, right? Okay, now, so there's another way of doing this, right? Because, I mean, why is he integrating? He could just take a Fourier transform, right? That's what you're all thinking, yeah? Why isn't he taking a Fourier transform? It's just actually, you'll see that when I end up having matrices, inverting that Fourier transform is very difficult. So what I'm going to do is, instead of, and it actually involves a lot of algebra. So what I'm going to do is I'm going to find, and I'm only interested for the moment at the correlation. So I have the correlation function at equal times. If I know the correlation function at equal times, I know it at all times later. But I want to calculate this guy here. So normally what you do, you could take the Fourier transform, right? You invert the Fourier transform, calculate the correlation function, right? And then integrate over omega to get the equal time guy. And then that has lots and lots of poles, and there's lots of algebra that you need to do. And actually see, you can directly get that correlation function without doing any integrals, Fourier integrals, okay? And you can see there's a sort of strange algebra that's born from these calculations. It's a nice algebra. So, so the other thing is, imagine right, this is e to k. Okay, so let me say, so I want to calculate the equilibrium correlation function. So if I want to get the equilibrium value, what I'm going to do is I want to be sure this thing is an equilibrium, right? So what I'm going to do is I'm going to make t finite, but I'm going to start the calculation at minus infinity, right? At the Big Bang. Okay? So I'm going to write the xi of t, if I do the formal, and the other thing is, so I'm going to start it at 0. I'm going to say the process is at 0 at minus infinity, right? So but it should have forgotten that it's at 0 at minus infinity, right? So it's just to avoid putting the initial conditions in my calculation. So I'm going to write the xi of t is equal to the integral between t and minus infinity. And there what you find is ds e to the minus t minus s times r of a. Okay, so this is ik here. Times zeta of k of s. Right, so I've assumed that x was equal to 0 at minus infinity. Okay, but I would have e to the minus r of a here anyway, so it would kill it off, right? So I'm just doing that just to, okay, so conditions. Not important. Okay, so now I want to take two of these guys. I want to calculate now xi of t, xj of t, right? Okay, so when I do that, so what I'm going to do is I've just got two copies of this, but they've got different indices. So I have an integral between t and minus infinity. Let me call the first ds, and I'm going to have another one which is ds prime, so this becomes a double integral. I have e to the minus t minus s ra. So this is the first guy, ik zeta k of s. And then I'm going to have e to the minus t minus s. So this is the second solution with the index j. So this is j, what am I going to call it? L zeta L s prime. This is s prime, okay? This is just the first solution. This is xi of t, and this is xj of t. Okay, so I'll just put them together. So now I want to take the average of this with respect to my noise. So remember that the noise had a correlation function which I wrote down here. The noise, I'm assuming it has this form, twice Rij delta of t minus t prime. So you can see that when I do that, it's going to set s equal to s prime, right? Because it's a delta function. So I'm only going to have one integral now. So I'm going to find that xj of t is equal to, so there's only one integral, so let me keep it as s. I'm going to have e to the minus t minus s Ra, this matrix. I'm going to have the component ik. I'm going to have e to the minus t minus s Ra, the component jl. And so I can put these zetas here together, okay? Because I'm using indices, they're just numbers now, right? So this is going to give me RKL, okay? And there's a factor of 2. And I've put the delta function in. Okay? Does everybody agree with that? It's not very complicated. So but this still looks like quite a horrible thing because, okay, so what I'm going to do, I don't want my R to be there. I'd like to have my R here. So what I'm going to do is I'm going to write this as twice the integral between t and minus infinity ds e to the minus t minus s Ra. So this is ik here. This is RKL. And then what I'm going to do is, you see, if I wanted to multiply these as matrices, okay, the problem is I want the L to be here, right? To go with this guy here, because I sum off the indices that come after each other. So what I'm going to do is actually I'm going to take the transpose of this matrix, right? So I'm going to take E, because it's real, actually, and if I were doing this calculation in Fourier space, I would be talking about adjoint matrices. I'm going to take Ra transposed, okay, and then I'm allowed to switch the indices. Everybody agree with that? No, let me not call it transpose. Let me call it adjoint. Okay, so if the matrices are real, then that's the case. If you do Fourier space, the correlation should become slightly different. But let me call it adjoint for the moment. So okay, so this is fine. So what is the exponential of x if I take the adjoint of exponential of x? Think of it as the transpose for the moment, right? If I take the transpose, okay? Well, that's just equal to the, yeah? So that's the first thing we're going to use. So what is x? Well, x is equal to Ra. So what is the adjoint of Ra? Yeah, so that's equal to A adjoint, R adjoint, right? Now look, R was defined as a correlation function of noise, right? So when I and J switch, it has to be symmetric. So, okay, so R is actually self-adjoint. Okay, so now I can write this in a nice way. I can write that C of T prime, so I use matrix notation now, is equal to twice the integral between minus infinity and t of e to the minus t minus s times Ra. I'm going to have R here. I'm going to have e to the minus t minus s. Now, if A was coming if A was coming from this model that I had here, right? This would be, because this is Hamiltonian, the Hamiltonian is going to be a symmetric, you're going to have a symmetric matrix. If I don't have a symmetric matrix, it doesn't matter, right? So A is obviously, for an equilibrium system, going to be symmetric, right? But I'm not going to assume that for the moment, even if because when we look at applying electric fields and we force the system out of equilibrium, what we're going to find is that A is no longer symmetric. It's no longer self-adjoint, okay? So things will change. So let me just abuse things slightly. So despite the fact I was selling this to you with an equilibrium in mind, let me just do this to keep things general, okay? So this is now, but now I've got lots, now I've got some problems here. I mean, I don't know if R commutes with A. I don't know if R commutes, okay, so I've got so how do I solve this equation now? So the thing to do, this is really why it's much simpler than doing, you pay a price, right? There's no such thing as a free lunch. If I'd done Fourier transforms, I'd have written the correlation function down by now, and I'd still be sticking my pen in my ear trying to work out what the integral is and counting the poles, right? And you can actually see that, when these are matrices, you can see why this is quite complicated. So look at this equation now, and let me take dc by dt. Okay, so this is a derivative d by dt of c of tt. So what's that equal to? So let me see where I've got t's in my problem. So everybody agrees I've got t's. I've got a t in this exponential here, a t in this exponential here, and a t here. So let's do the t in the integral first. So if we just differentiate the integral, so the first term is going to give me 2. So I evaluate this. When I take the derivative, I evaluate the integrand at s is equal to t. And you see something nice happens is that these two beasts disappear because t is equal to s. So differentiating with respect to t sets s equal to t here, so I just get 2r. Okay? Now what happens if I differentiate the first, who can tell me what happens if I differentiate the first exponential? See, if I differentiate the first exponential, it gives me RA, right? It gives me RA times the exponential. So it brings out a factor of RA on what side? If I differentiate with respect to this t here, do you all agree the only thing that happens, when I differentiate it, I can bring it out either side. So I'm going to bring it out on this side, right? So this is just giving me, but that was just C, right? So that's just RA acting on C. And there was a minus sign, right? So it's minus, check. Is that right? There was a minus sign. It's minus t when you differentiate. So it's minus RAC. Yeah, that's right. The Royal Automobile Club, right? And then if you differentiate with respect to the second guy, what happens is it brings out A dagger times R, but I'll bring out A dagger times R on that side, but that's just C. Okay? Okay? So in the steady state, oh yeah, C is to the left, good, yeah. Okay, yeah, that's the point, yeah, it's on the left. Okay? So actually, so this looks like a lot of horrible algebra, but sort of if you do it with Fourier transforms, you get into even worse states. So in a steady state, equilibrium, if we have the right sort of A, if A is symmetric, right? Well, this guy is equal to 0, right? That's the definition of a steady state, right? That quantities that depend on a single time, one of the properties of the steady state was this must be 0, right? Statistics don't evolve with time, so averages can't evolve in time. So we actually find the equation of Gauss, which is RAC minus C A dagger R is equal to twice R. Plus, what am I talking about? It's a plus. Yes, it's a plus. Okay, is equal to 2R. That's your equation. Now, what happens if I had an equilibrium system? If A is equal to beta times some matrix delta, okay? So for an equilibrium system with a quadratic Hamiltonian, that means that B, and so A and delta is symmetric, right? So if it's real, delta is equal to delta dagger, then what you're going to find is that you write this equation as beta times delta C plus C beta, so R delta C plus C delta R is equal to twice R. Now we know what the solution is, right? We saw before that C must be equal to T divided by delta to the minus 1. Okay, and if I put that solution in, you see it works, because delta to the minus 1 gives me T here, which cancels with the beta. Delta to the minus 1 here cancels with this guy here, and so it gives me R, so I find the right solution, okay? That's trivial, okay? But in general, you get equations which are much more complicated, right? So these are interesting equations. Okay, so you have these matrix equations, and so if you look at electrolytes, you actually see that these become matrix equations. If you look at two species, then you have 2 by 2 matrices, because you Fourier transform. Things become diagonal in Fourier space, okay? So that's a very general result. So if you want, so you can look at Gaussian processes, so you can look at, Langevin systems which are driven by matrices which are not symmetric, okay? So it's a very simple out of equilibrium system to study, okay? So that's the... Okay. Sorry? Oh, sorry, yeah, C is T by delta. Yes, so sorry, I should have done, I was overkill there, right? C delta to the minus 1. Okay. Okay, now, so now if I go back to my theory, if I write down the stochastic density functional theory, I can actually predict what the, so I can look at n tilde of k of t, n tilde of k of prime of 0, okay? And that's equal to 2 pi to the d. This is right, okay, I've got another mistake in my notes, okay, that's fine. Delta of k plus k prime times, you can write down a dynamical structure factor, okay? So S of k of t. So in t equals 0, it's the usual static structure factor, okay? So if you look at that, and you look at the form of R in my equation, right? In my equation, the term with the noise was, it was the divergence of, we had d times rho bar, okay? So this is the noise term. In the linearized stochastic density functional theory. So in Fourier space, if I take in Fourier space, this is going to become ik d rho bar. Sorry, it's the square root of 2 d rho bar, okay? So it becomes ik scalar product with eta tilde, square root of 2d rho bar. Okay? And if I work out in Fourier space what its correlation function looks like, this noise, this zeta tilde of k prime, takes the form 2 pi to the d delta of k plus k prime, 2d rho bar. And when you work out this correlation, you have a k prime and a k, but you have delta of k plus k prime, so it basically gives you k squared here. Okay? So basically in Fourier space, acting on the Fourier modes, actually, the operator r tilde of k looks like, if I take the Fourier transform, the original equation, it just looks like k squared rho bar times d. So that's my form, that's the form of my r. So basically this tells me that sk of t is equal to, so when I was working out my correlation function, well, we know we have the static structure factor, right? And then this is just multiplied by e to the minus, so it's e to the minus t r tilde a tilde. And we saw that a tilde was beta, a tilde had this form here, it's equal to beta times delta. And we also saw, you can check, if you write it in terms of the structure factor, you find it's e to the minus t, rho bar d, k squared, divided by S of k. Okay, so that's the prediction for the static density functional theory. Okay, so now the thing is, I showed you that S of k I had an approximation, right? I said that S of k was equal to rho bar divided by, S of k was equal to rho bar divided by 1 plus rho bar beta d tilde of k, right? But actually, if you talk to somebody who's doing an experiment, right, then you can say, well, okay, I can correct my theory. So you don't necessarily have to use this, right? So what you can actually do is you can use a theory where you take a V effective to give you the result, the correct static result, right? So you can sort of patch up your theory. Okay, so you can use V effective to get the correct static flux. Okay, so these are the predictions of the theory. So you basically have some exponential decay, and what I'm going to show you is, okay, so the theory, the decay of this object at late times, it doesn't predict things very well, but at short times it's exact. So in principle, if you use this, you have a theory which tells you you can make the structure factor exact, and what I'll show you as well in the next lecture, or perhaps as an exercise, I should show you in the examples class, how you can actually show that this gives you the exact short time behavior. And the other thing which is important is that if I look at free Brownian particles, right? If I look at free Brownian particles, it gives the exact result for free Brownian particles, which is not obvious that it works, because actually one of the strange things is that, see, if I look at the free case, so it gives this is exact for free particles. So you think, well, okay, big deal, free particles. Well, let me just go back to my equation for the free particle equation. So I'll write down d rho by dt is equal to d times Laplacian of rho, and I write down my noise. So that's the stochastic density functional theory for free particles, right? Now, if I showed you that, and I said, can you solve that theory? You'd say, no, it's a horrible, shitty theory. Sorry, I put the rho in. Okay, you could solve that one. But if I put the full rho here, right? If I asked you, could you solve that theory? You'd probably, no, what would you say, Abhishek? You look at it and you say it's got multiplicative noise, and you would say, well, yeah, so if I can write down the KPZ equation, I can write down, well, Gaussian theories, I can always solve them, right? But there are lots of, stochastic burgers and things like this. There are lots of theories that you would like to solve, but you can't solve them exactly. If this was somehow given to you, right, as an exam question, solve this stuff, you just leave, right? You think the examiner's taking the mick, right? But the funny thing is that you know exactly what the statistics of this row are. You can compute all of the moments. So it's strange. So you have so in principle, you have a highly non-trivial partial SDE with multiplicative noise. And because it's free Brownian particles, you can compute the statistics of the density field exactly, right? So if you want to work out what the moments of this thing should be, it's easiest just to take rho tilde is equal to the sum over the particle numbers, I is equal to 1 to n, okay? So let's have a look. I can start, if I start the time at time t, I get e to the ik. My Brownian motion is, so basically if I integrate this, so this is square root 2t, so this is just, so you have 2d times the standard Brownian motion, right? Plus some initial coordinate, so this is I, bi of t, and you have some initial coordinate xi of 0, right? So this is what the density field would look like. So you start off at time 0 with all the particles. If they're non-interacting Brownian particles, right? Then if they're in some volume, they'll have a uniform distribution, right? So there are two informations. So there are lots of solutions to this equation because I can take any value of xi of 0 in principle, right? This solves this equation. So you can compute its moments. So you can, notably, you can compute the second moment, right? I mean, the thing is, and you can compute the third moments and things like this. So what we can see is that if I compute this first moment here, the second moment, sorry, for free Brownian particles, it gives me the exact correlation function. Okay? So that's another good point about the theory. So are there any questions? Oh, sorry. So actually, so this is just this Fourier transform of my density, right? So let me have a look. So let me just, yes. So how did I get this? So yeah. Now my equation, my stochastic equation is just dxi is equal to the square root of 2d times dbi, right? Plus, well, that's my equation, right? I'm looking at this system here. So I do the whole calculation I did before. There's just no potential. So I get this equation, right? So there's no v in here. That's the only difference, okay? So if I integrate this equation, this tells me that xi at time t. If I integrate the Brownian motion, this gives me 2d. Then I integrate the Brownian motion, so I just get some Brownian motion evaluated at some time t, right? And I have to have the initial condition. I put in some little xi of 0, okay? Okay, so I put this in, okay? So I know what my solution is, but obviously I mean, it's just easier to do the calculations in Fourier space, right? If I look at rho tilde, that's equal to the integral of the density field, which is the sum delta of x minus xi e to the minus ik. Did I put the minus sign in? Depends how you define your Fourier transforms, okay? So this, when I do the Fourier transform, this is just equal to the sum over all the particles, I is equal to 1 up to n, e to the minus ik xi, right? It's just, if you want to work out these moments, right, it's a bit horrible to work them out with the delta functions. Or you can work them out with the delta functions, but once you go to higher moments, it's easier to do all the calculations in Fourier space, okay? So this is rho tilde of k as a function of time. Okay, and actually what you can do as well is an interesting exercise, is actually if you want, you can actually start off with this equation for rho tilde, and you can actually write down the stochastic differential equation for rho tilde, and what you'll find is that you'll actually end up getting the Fourier transforms of this equation. So if you were unhappy and you lost sleep last night because I was differentiating and doing horrible things with delta functions, then actually if you do it in terms of Fourier, the Fourier transform, then everything is nice and happy, okay? So this theory is interesting. So you can, because you're only doing a small v expansion. So one way of correcting it is to really use the structure factor here And then this gives you, and this also gives you the exact short time result and the exact result for free particles, which isn't obvious from looking at this, okay? And so people have tried to solve these equations directly, okay? There are papers where people try and look at the field theory of the free case, and it's incredibly complicated, okay? But you know the solution. You can write down the path integral. I'll show you how to write down the path integrals for this. It's sometimes in maths people find strange identities because you do a calculation in one area and then you do a calculation in another area, and then you actually find that these two things must be the same, right? And you can't actually, so you can go from A to C and from B to C, but it's not clear how you go from A to B directly. So this is a way of seeing that this is, this equation, despite the fact it looks horrible, you have a whole class of solutions that you can generate, which is quite rare for this sort of equation, right? They've only got 3 for KPZ, no? So, okay, any other questions? Lunch then, okay.